Greetings, everybody. So today we are going to discuss about our new topic, which is the one shot of chapter number six, chapter number five, which is the liquids. So here we are going to first discuss about the basic characteristics of liquids on the basis of the kinetic molecular theory, which was collectively proposed by a number of scientists such as van der Waals, as well as Clausius, as well as some other scientists were there as well. Now, coming to the point that kinetic molecular interpretation of liquid, what does it say? It first and foremost, the point which it says that it is, liquid molecules are close together. They are close together, having small spaces among them, such that we previously studied in gases. In gases, there were the molecules which were far apart from each other. They were far apart from each other, while in solids, the molecules were very closely arranged with each other. But when it comes to liquids, liquids are neither too far from each other, neither too close to each other, which means they are in between both of the ranges, such that they have small spaces among them and are close together. And liquid molecules are in constant motion. Liquid molecules are in constant motion, but their movement is restricted, such that if there is water molecule, let's suppose this is hydrogen, this is hydrogen, and that is attached to a molecule of oxygen, let's suppose. So at that moment it is in constant motion, and it is in constant motion, but it is restricted by the attraction, or the forces of attraction, which are also known as the van der Waals forces, causing to restrict its motion. So restriction of motion is also caused by van der Waals force. Here we are going to discuss that. Now these are weak attractive forces present among liquid molecules, very weak attractive forces. These are attractive forces, but these are weak attractive forces as compared to solids. And we are what how are they weak, we are going to discuss as well. Number four, here is the collision among liquid molecules are more frequent, such that they have more frequent collisions. Brownian motion is the result of unequal number of collision of liquid molecules from each other from different sides, such that if there's unequal collision, then it leads to Brownian motion. We have previously studied that there is chaotic motion or irregular motion, which is known as a Brownian motion, that occurs in cases of uh, gases, but in cases of liquids, it would be considered as a collision of liquid molecules with each other from different sides, which will also lead to an irregular motion. And collision among liquid molecules are more frequent, such that their collision is more frequent because of more kinetic energy. Collision among liquid molecules is uh, frequent because they are close to each other, as well as because they have moderate kinetic energy and moderate uh, closely arranged with each other. Moreover, unlike gases, they do not show appreciable contraction or relaxation, contraction or expansion by heating or cooling. Like, we can study the properties right now, such that number one is diffusion. That whenever two gases are diffused, what does diffusion means? Diffusion means miscibility, mixture of miscibility, such that the higher miscibility moves towards the lower miscibility within a mixture of miscibility. Such property was considered as diffusion. In order to diffuse or spread out or escape or diffuse, or in a sense that causes to spread out or within a larger space, which is known as diffusion. So at that moment diffusion was defined properly in gases chapter, but here when it comes to diffusion in liquids is slower than gases. Reason behind it is that it is liquids are having high amount of intermolecular um, forces. They have intermolecular forces of attraction, due to which there is small intermolecular gap, which causes difficulties in flowing of the liquid molecular movement, as a result of which a drop of ink spreads in a glass of water slowly. Now again, diffusion depends on certain factors such as intermolecular forces. If there is a liquid which is having high amount of intermolecular forces, strong intermolecular forces, that would be having uh, less diffusion rate. If there is high temperature, then there is more diffusion rate. So these are some factors to be considered as well. Compression. Liquids are very less compressible as compared to the gases. In terms of kinetic molecular theory, liquid molecules are in constant motion in small intermolecular spaces. Hence, if we put pressure on liquid, its volume does not appreciably change. Example of this is the hydraulic brake system, which is due to the liquids. And here, in that case, there's also the work done in it. The work which is done in that case is a pressure volume work, which leads to uh, you know uh, run the piston while utilizing the hydraulic brake system in the automobile. Anyways, it's a separate topic. And here, um, basically that also involves the mechanism of pressure volume work, and at that moment there is also compression, but that compression is really negligible, and in order to accompany, in order to attain that compression, there is requirement of doing a lot of amount of work, and as a result there would be a lot of amount of pressure generated, due to which it is adequate to stop the brake of the car. As a result, so brake of the car can be stopped because of the compression or high viscosity of the liquid or the fluid present within the piston. Now, expansion and contraction, liquids expand on heating. However, they do not show appreciable increase in their volume by heating like gases do. Expansion is due to high kinetic energy of molecules at the higher temperature, which result in the separation of molecule and creation of molecular gaps, such that they are separated from each other and create a molecular gap between them. Contraction is opposite of that. It takes place by lowering the temperature or cooling, in which the molecule of liquid at lower temperature lose kinetic energy and come closer together. When it comes to the molecular motion move liquid molecules move randomly in all possible direction. However, due to small gaps and attractive forces, speed of molecules is slow as compared to gases, such that gases are having higher speed, liquids are having lower speed. Moreover, when it comes to kinetic energy of liquid is lower as compared to um, gases, because gases uh, are in more of the gases are in more of the unstabilized state, and liquids are in more of the stabilized state. Likewise, when it comes to solids, solids are the most stabilized. So as solids are the most stabilized, they are having the amount of kinetic energy to be less. On the other hand side, when it comes to gases, gases are having the amount of kinetic energy to be very very high. Likewise, when it comes to the potential energy, on the contrary, if the kinetic energy in the gases is quite high, then the potential energy in the gases would be ultimately lowest, and the kinetic energy as in solids is very low, will be having potential energy in the solids to be highest, as a result of which stability will be most in the solids, reactivity would be less least in the solids. Likewise, stability would be least in the gases, and reactivity would be most in the gases. Likewise, we can also consider using this phenomena some other characteristics properties, physical properties of liquids, such that if there is low intermole, if there is a solids, and there we know that in solids there is um, high amount of intermolecular forces, high stability, less reactivity, which means there will be high melting point, high boiling point, high stability, as well as there will be uh, certain properties such as high amount of in case of liquids, if there is a more denser liquid, if there is more a stronger intermolecular force containing liquid, then at that moment it will be having more viscosity. If a liquid is having more amount of intermolecular forces, stronger intermolecular forces, high melting point, high boiling point, high amount of vapor pressure would be generated. As a result, high melting point, high boiling point, high viscosity would be there, high surface tension would be there, as well as there will be high amount of polarizability at that moment. So in this cases, this would be the consideration. On the other hand side, if we talk about other characteristics, uh, if a liquid is having less amount of intermolecular forces, at that moment there will be less more melting point, less boiling point, high amount of vapor pressure, high amount of evaporation, less amount of surface tension, less amount of viscosity, as well as less amount of stability, high amount of reactivity. So these are the factors which we consider. Apart from that, intermolecular forces in liquids, such as van der Waals force, these are the forces which we also call as uh, physical forces of attraction, secondary forces of attraction, van der Waals forces of attraction, or intermolecular forces of attraction within the liquids. And these forces basically are the attractive forces, and generally these are electrostatic in nature. One more thing, that these intermolecular forces of attraction define, first we need to understand what is the primary force. Primary force of attraction is in actual the force which defines matter, that what actually the matter is, what is the characteristic of that matter. But when it comes to the secondary forces are responsible to define the state of matter, such that if the matter is having that primary that secondary force, then whether it would be a solid, or it would be a liquid, or it would be a gas. Just like if we talk about H2O, H2O is having the H2O is having a bond, secondary force of attraction, which is known as hydrogen bonding. We all are known about it, hydrogen bonding. And that hydrogen bonding, if we consider H2O having no hydrogen bonding, we'll simply assume that H2O will have the state of matter as a gas, because in gas state there is no hydrogen bonding, which means it is in the form of a vapor. Likewise, if we talk about H2O in the form of a liquid, then we will be assuming that there will be less amount of hydrogen bonding. But again, if we talk about considering the H2O in having maximum amount of hydrogen bonding, then at that moment we will be considering it in the form of solid. So in this case, these are some considerations, but again there are some exceptions which we are going to discuss in the upcoming part. And here what we are going to discuss about five major forces, five major van der Waals forces, five forces. I would like to just give the brief intro of all five these. First thing is dipole dipole, dipole dipole interaction, dipole dipole interaction, dipole ion interaction, dipole induced dipole interaction, induced dipole interaction, and number four is induced dipole instantaneous dipole interaction, which is also known as induced dipole instantaneous dipole interaction, which is also known as London dispersion force. London dispersion force. And after that, we are finally having the hydrogen bonding. Hydrogen bonding is in actual the type of dipole-dipole interaction. Uh, when we consider all of these five forces, we need to first understand what actually these are. When it comes to the first part, which is dipole-dipole, what does the word dipole resembles, and what does the word dipole signifies here? So the word dipole here signifies that here we know that what is a dipole? Anything which is having two pole charges, which means anything which is having two charges is known as dipole. Let's suppose if we talk about any compound like HCl. Let's suppose this is HCl. Now HCl is will now, if we consider the structure of HCl, that here HCl is having its electronegativity. HCl is having its electronegativity as 3, which means it is a higher electronegative. And on the other hand side, if we talk about uh, hydrogen, it is having lower electronegativity, which is 2.1. Now these are the electronegativities of HCl and hydrogen and chlorine and HCl. Now in this case, when we are going to find the electronegativity, we will be able to understand that one which is having the highest electronegativity will tend to pull more of the negative charge towards it, which means the electron which would be shared between both of them will be in a manner with the electron which is shared between both of them will be now attracted more towards the more electronegative atom, because the more electronegative atom has more electronegativity or the capability or the power or the power or the candle in order to attract the electron towards it. So in that case, the electron will come more towards the chlorine, less towards the hydrogen, due to which chlorine will ultimately gain a partial negative charge and hydrogen will ultimately gain a partial positive charge. So this molecule which is having two partial positive and partial negative charges, or two charges in general, is known as dipole. Now if we talk about an interaction which is formed between a dipole and another dipole, let's suppose this is one dipole molecule, this is a covalent bond formed between them. And let's suppose if we have another dipole, um, let's suppose if there is another dipole, uh, again HCl, right? So here there is another dipole HCl, same. There is consideration of partial positive charge on hydrogen, partial negative charge on chlorine, such that when both of these dipoles are having partial positive and partial negative charge, what actually will happen over here will be a physical interaction, an interaction which would be formed due to some sort of electrostatic attraction. and that's electrostatic attraction which we developed in between the chlorine of HCl of one dipole and partially positive hydrogen of another dipole, such that partially negative chlorine of one dipole will tend to create an interaction with the partially positive hydrogen of another dipole, due to which there will be formation of a interaction, a physical force of attraction, which would be known as a dipole dipole interaction. This is known as dipole dipole interaction. When it comes to its theoretical part, here it is around 1%, or its strength is around 1% that of what we call as the covalent bond, which means it is it's still it is a weaker bond as compared to the chemical forces of attraction, because chemical forces of attraction are stronger ones. Now when it comes to other part, if we take the same example, and let's suppose if we take the example of, oops, so here, as you can see, this was the first part in which dipole was formed. Second is dipole ion interaction. What does it refers to? Let's suppose if we have a solution, let's suppose if you are having a beaker in which there is 1 decimeter cube of water, 1 decimeter cube of water in a beaker. If there is 1 decimeter cube of water in a beaker, now at that moment, if I'm supposed to add an a salt, a neutral salt, which is NaCl, when you're going to add the NaCl salt into the water, what actually will happen over here, there will be an interaction formed. There will be an interaction formed between the H2O and NaCl, such that NaCl will dissociate itself into ions. NaCl will dissociate into its ions, which is known as sodium ion, first and foremost, and second includes the chloride ions. Now, when sodium and chloride ions will tend to dissociate within the solution, it will tend to move freely within the solution. Just like, it will tend to move freely within the solution. As it will tend to move freely within the solution, now that will lead it to form again a force of attraction between sodium. Let's suppose this is sodium, and on the other hand side, if there is chlorine, and on the other hand side, we are having H2O, which is having partial positive and partial negative charge, such that H2O has a structure in such a manner that O is more electronegative, due to which electrons will be more attracted towards the oxygen, due to which it will gain and acquire a partial negative charge. On the other hand side, hydrogen will acquire a partial positive charge, likewise, because of less negative charge towards it, less electron share towards it, due to which there is less electron share, due to which it will have a positive, it will have a negative charge. Now coming to the point here, that when there is a positive charge, partial positive charge, hydrogen, partial negative charge in oxygen, the negative end of one dipole, basically it's a dipole, so negative end of one dipole will now tend to attract to the positive ion, which is formed due to the dissolution of the neutral salt, and the positive end of the other dipole will tend to form a force of attraction with another ion which was formed by the dissolution of the neutral salt, as a result of which this force of attraction which is formed between a dipole and an ion is known as the dipole ion interaction. Now we are going to discuss their strengths as well, how strong they are. This is the concept. After that, when it comes to some other example, let's again discuss the same thing. Here we are having, let's suppose, if there is HCl. Now, if there is an HCl, basically it is a polar molecule. It is a dipolar molecule. It has two charges, so it is a polar molecule. Partial negative charge, partial positive charge, partial negative, partial positive charge, such that when it will tend to, if we are going to put it somewhere with a non-polar molecule, it is a polar molecule, polar, molar, polar molecule. On the other hand side, if we are supposed to put it with a non-polar molecule, non-polar molecule, and let's suppose this non-polar molecule is chlorine gas. Let's suppose chlorine, because it is non-polar, chlorine HOMO molecule is there. There is no electronegativity difference, due to which it will have non-polar nature. So it is having a polar non-polar nature. Now when we are going to put HCl and chlorine gas together in the same container, now here there is a dipole and here there is a non-dipole or non polar molecule, such that when dipole will come near with the non-dipole, the dipole's negative charge, either the dipole's negative charge or the positive charge, the negative charge of the dipole will tend to attract uh, the negative charge either or the positive charge either. The positive charge will tend to attract the negatively charged electrons. Negatively charged electrons, let's suppose these are the negatively charged electrons within its orbit. Negatively charged electrons within its orbit, such that, let me, 1 2 3 4 5 7, right? So these are the negatively charged electrons within its orbit, such that when uh, the electrons such that these electrons, which are now, these are negatively charged, of course. So when there is a partially positive charge accumulated over the HCl, that partial positive charge will tend to attract the negatively charged electrons of the chlorine towards it, as a result of which, on one hand side of HCl, on one hand side there will be more accumulation of electrons, on another side there will be less accumulation of electrons, such that as there will be a attraction, there will be attraction of the partially positive hydrogen, due to which the electron cloud which is in circular shape here, the electron cloud which is in circular shape now will tend to change its shape, which means the electron cloud will be distorted, such that this is electron cloud in circular shape, it will be now distorted in such a manner the shape will be distorted, and many of the electrons will be, you know distorted due to the distortion of the electron cloud, and that electron cloud distorted will cause to form an asymmetrical, previously it was a symmetrical cloud, now there was asymmetrical distribution of electrons, such that on one hand side there is more presence of electrons, on the other side there is less presence of electrons, due to which this will lead to an imbalancement in the, or asymmetry of the electrons, due to which we can simply call this as this phenomena as the electron cloud distortion. Here, the electron cloud distortion occurs. After the electron cloud distortion, the electron cloud distortion, the density, electron density is asymmetrical, because on one hand side there is more concentration of electrons, on the other side there is more concentration of electrons. As a result of this distortion and asymmetry, this asymmetry will lead to accumulate partial negative charge on one hand side of the non-polar molecule and partial positive charge on another side of the molecule, which will cause to form an interaction between both of uh, the polar and non-polar molecules, such that polar and non-polar molecule will now develop an interaction between them, which would be known as the dipole induced dipole. But here, as there's partial negative charge, partial positive charge due to the asymmetry of the electron cloud of the non-polar molecule, it will lead it to, now convert it into a polar molecule with partial positive, partial negative charge, known as an induced dipole. Induced means produced, which means it is produced dipole, and that produced dipole is produced due to the interaction of dipole. Now, when dipole and induced dipole will tend to interact with each other, that will form a dipole induced dipole interaction. Now, this is about this. Now, when it comes to hydrogen induced dipole, instantaneous dipole interaction, it is in such a manner that, uh, let's suppose if we are having two non-polar molecules. Let's suppose if there is chlorine on one hand side and nitrogen on another hand side, let's suppose. And now what we are going to do actually, or better to do it with a single molecule, otherwise, that will, according to our syllabus here, chlorine and chlorine. Now both of these are non-polar molecules, both of these are homomolecules, both of these are same. Now what we are going to do is to, provide them the conditions of liquefaction, such that we know that whenever we are going to liquefy a gas, we provide them the condition with low amount of temperature, high amount of pressure. so that they can liquefy into liquids. And as they will liquefy, that will this methodology will be known as Lind's methodology, which we have previously studied as well. Lind's methodology. And one more thing, that here you might have wondered that what kind of forces are there which would hold the liquid molecules, which would hold the gaseous molecules when they're converted into liquids. So the reason behind it is that the forces which are actually formed there are the London dispersion forces, or the induced dipole instantaneous dipole interaction forces. Let's discuss how. Let's suppose if you're providing them the low temperature high pressure condition. At low temperature, it will cause to, you know, release the kinetic energy, decrease the kinetic energy of the gaseous molecules. As a result of decrease of the kinetic energy of the gaseous molecule, it will cause the kinetic energy of the gaseous molecules to decrease, the due to which the molecules speed will start to slow down, which means the collision rate will start to slow down on one hand side. And on the other hand side, as there is high pressure developed, high pressure will cause the molecules to come closer to each other. As a result of high pressure, they will come closer to each other, as a result of which they will tend to, start to develop several forces of attraction between them. And at that moment, when they will tend to come closer to each other, what actually will happen there is that, let's suppose if there is one chlorine, this is one chlorine, right? One chlorine. Let's suppose this is chlorine molecule. Now, let's suppose the molecules are quite closer to each other due to high pressure, as well as there is low kinetic energy due to low temperature. Or and now, as these are very closer to each other, this closeliness with each other, the molecules will now, being closer to each other, will tend to, let's suppose these are two molecules which are very close to each other. Now we know that these molecules are basically having electrons in their outermost shell, electron cloud, which is surrounding them. Now when electron cloud will be surrounding them, will be brought too close to each other, they will now tend to repel each other. Just like if we are having two electron clouds, one electron cloud and on another electron cloud, both of these are having electrons full of them, that will cause to repel both of the clouds of electrons due to negative charges accumulation, as a result of which the shape of the electron cloud will again distorted. It will be distorted in such a manner that on one hand side there will be more concentration of electron, other hand side there will be less concentration of electron. Likewise, on one hand side, uh, there will be high electron density, other hand side there will be less electron density. Or in other words, we can say that the electron density will become asymmetrical. Previously it was symmetrical because charges were distributed equally on all sides, but now it is asymmetrical because charges are distributed unequally on each and every side, right? So this is how this distortion will occur. And due to asymmetrical electron density, one side will have more positive charge, other side will have more negative charge, due to which it will lead to form uh, a dipole at a given instant. It is not a dipole in actual, but it is a dipole which is developed at a given instant due to high pressure and low temperature. And that dipole which is developed at the given instant is known as instantaneous dipole. Instantaneous dipole. And once that instantaneous dipole is developed, what that instantaneous dipole will do will cause the other dipole, the other nonpolar molecule. Let's suppose one dipole is developed over here, just trying to draw a distorted structure. One dipole is developed over here. On the other hand side, if there is a nonpolar or non-dipole. Now, when the non-dipole will come near the instantaneous dipole, that instantaneous dipole will also cause a distortion of the other dipole, due to which it will be distorted. Its electron cloud will be distorted. Electron density will be mismanaged. I mean, unequalized, due to which there will be asymmetrical electron density, and thus it will again gain a positive as well as a negative charge due to attraction of the electrons. Uh, you know because reason behind it is that the electrons of this cloud will now, due to negative charge, will repel on the other hand side, negative charge will be accumulated on the other hand side, and positive charge will be accumulated on this side, due to which this is how another dipole which will be formed due to instantaneous dipole, which would be known as induced dipole. And that induced dipole formed due to instantaneous dipole will be now known as the induced dipole. And now there will be a force of attraction generated between both of them, and that interaction would be known as the induced dipole instantaneous dipole interaction, or London dispersion forces. London dispersion forces because it was named after the scientist who gave introduction to these forces, and his gentleman name was Fritz Haber. We are going to Fritz London. Sorry, he was a scientist, a very famous chemist. It's here as well. Yes, Fritz London, who was a German physicist. And here, apart from that, when it comes to the hydrogen bonding, we are going to discuss that as well. First, we should go for the reading. Here, as you can see, liquid molecules are either polar or non-polar. They appear partially positive, partially negative charge. HCl is a polar molecule, and there is a partial positive and partial negative charge. The electrostatic forces of attraction between the positive end of one polar molecule and negative end of the other polar molecule is called dipole-dipole interaction. As a rough comparison, their strength is about 1% of the normal covalent bond. An example of liquid in which dipole force exists is called iodine monochloride, reddish brown oily liquid. The more electronegative chloride atom possesses partially negative charge, whereas less electronegative iodine has partially positive charge. The partially negative chlorine terminal of one molecule is attached to the partially positive terminal of iodine on the other molecule. So this is a brief intro, and here in our book it's not given about the five forces, but it was an additional one. And London dispersion forces. These forces were first reported by German physicist Fritz London. These attractive forces exist among non-polar molecules which become polar temporarily. Nevertheless, we are having gasoline, benzene are non-polar molecules but exist in liquid state at room temperature due to the presence of London dispersion forces. These are the weakest physical forces of attraction, and the strongest one are the hydrogen bonding. How? And we are going to draw the chart as well. When non-polar substances such as hydrogen, chlorine, fluorine, helium, neon, argon are allowed to liquefy by lowering the temperature, a temporary interaction is developed among their molecules due to the distortion of the electron cloud of one atom by the electronic influence of the other atom. This makes a short-lived polarization and is said to be instantaneous dipole. The instantaneous dipole then distorts the electron density of the nearer atom and hence produces an induced dipole in the nearby atom. And the attractive force which is developed between an instantaneous dipole and an induced dipole is known as the London dispersion forces. And some characteristics which influence the London dispersion forces are two, which includes the size of atom and the atoms in the molecules. Now, what are these? We are going to consider right now. So here, as you can see, that uh, there are certain forces which are developed between induced and instantaneous dipole, which are known as the London dispersion forces. Now, London dispersion forces is dependent on two major factors, among which number one includes the size of the atom, and number two is the number of the atoms. Such that if we talk about the size of the atom, now if the size of the atom is larger, if we are considering on one hand side hydrogen is having a smaller size. On the other hand side, if we are having, let's suppose, argon, argon is having a larger size. Now if we talk about both of their sizes, argon is having a larger size. Now when argon is having a larger size, it will be having high amount of atomic radii, which means that if it is having larger size, it is having less nuclear force. As a result of less nuclear force, as there is less nuclear force, there will be a higher. If there is a less nuclear force, then at that moment, if there is a less nuclear force, sorry. So here, argon is having a larger size. So larger size will lead to have a less nuclear force. As a result of the less nuclear force, the argon will be more capabilized to have polarizability. Polarizability simply means polarization, which means formation of the two charges or two dipoles. Here, now, as there will be less nuclear force, there will be polarizability. There's more chances of causing it to become polarizability because it is less nuclear force. Less nuclear force means that it is less stabilized. Less nuclear force, less stabilized, less stable. because of less nuclear force, and more reactive, less stable, more reactive, right? So this is what we consider over here: less stable, more reactive, due to which it will tend, it is most less stable due to less nuclear force, due to which it is more likely to polarize its electron and allow the electronic distortion, or the distortion, or in other words the asymmetrical asymmetry of its electronic density, as a result of which there is more possibility of larger size atoms to have electronic cloud distortion, and ultimately the asymmetry of the electronic density because of the high amount of size, which ultimately leads to less amount of nuclear force present between them, due to which it is easier to distort the electrons out and ultimately cause asymmetry of the electronic density. When it comes to hydrogen, on the other hand side, hydrogen basically it is having smaller size, due to which it is having high nuclear force. Due to high nuclear force, it simply means that as there's having high nuclear force, this high nuclear force will tend to make it more stabilized, such that due to high nuclear force, it will now, whenever we are going to distort it, its electronic cloud will be less distorted, less. Reason behind it is that it is having high nuclear force, due to which it will be distorted less, and as a result of that less distortion, there will, as a result of this less distortion, it will be having less distortion. As a result of less distortion, as a result of less distortion, and less chances of causing it to become polarized by distorting the electronic cloud and causing asymmetry of the electronic density, there will be less chances, or the London dispersion forces developed will be weaker, and the London dispersion forces developed here will be stronger because of the more chances of developing high atomic size, due to which there will be less nuclear force, and that will of course affect the London dispersion force in larger atoms. Likewise, if we talk about a larger number of atoms, if there are more number of atoms, then there will be a stronger if there is more number of atoms, let's suppose there are two or more, let's suppose if we are drawing many number of atoms which are currently uh, packed in a container. If there are more number of atoms in the container, then there will be less space, which means they will be more closely packed with each other, more closely remained within the container, due to which there will be more chances of polarizability or distortion of the electronic cloud, and ultimately the asymmetry of the electronic density, which will lead to the following conditions. Now, this is a basic factor, considering it, apart from which, when it comes to some other factors, we are going to discuss it over here, such as, hydrogen bonding. Hydrogen bonding is a vast topic, which we are going to cover over here just in a while. Yes. So here, as you can see, now we are going to discuss about hydrogen bonding. Hydrogen bonding basically it is also a type of dipole-dipole interaction, but it is basically a bonding which is considered as a strong form of dipole-dipole interaction, such that it is a bonding which is formed between an electropositive atom, which means partially positively charged, or a less electronegative atom, which is known as the hydrogen atom. On the other hand side, we are having uh, a highly electronegative element. On the other hand side, we are having a highly electronegative element. In case of dipole-dipole interaction, DD, dipole-dipole interaction, we basically had less electronegative element, which means there was a electronegative element which was more electronegative than hydrogen, but that formed, the difference which was coming between hydrogen and that electronegative element was less, due to which electronegativity difference was less in these elements: bromine, chlorine, as well as, let's take example of iodine, let's take example of sulfur, right? These had weak hydrogen bonding, weak amount of interaction with hydrogen. So but when it comes to interaction of hydrogen with uh, elements such as oxygen, nitrogen, and fluorine, these are highly electronegative elements, such that fluorine is the most electronegative element in the entire periodic chart, nitrogen a bit less than that, and oxygen a bit less than that. So in that case, here oxygen has around how much? It is around 3 point something, 3 point, and here it is also having less than, nitrogen is having less than oxygen. So these are the electronegativities, and in that manner we can say that whenever there is a force of interaction which is formed between, let's suppose we can take the example of oxygen with hydrogen as H2O, oxygen, fluorine with hydrogen as hydrofluoric acid, and nitrogen with hydrogen as ammonia. Let's suppose these are the uh, compounds. And here in this case, um, let's take example of H2O. So in H2O, what we are going to do here is, check that here, as we can, as there is presence of one oxygen, that oxygen is bounded to the H or hydrogen in such a manner that here there is one bond, there is another bond angle 104.5, bond angle 104.5, right? These are the lone pairs two lone pairs. Likewise, there's another oxygen molecule, two lone pairs. This is hydrogen, this is another hydrogen. Now whenever there is a force of attraction which is formed between one the less electronegative hydrogen atom with of one molecule with the lone pair of highly electronegative element of another molecule, then this type of interaction which is formed between the less electronegative hydrogen atom with the lone pair of electrons of the highly electronegative atom of an other molecule is known as a hydrogen bonding, such that when there will be a force of attraction which would be formed between this hydrogen and the lone pair of highly electronegative atom, let's say oxygen, then at that moment there will be a force of attraction developed between both of these, which would be a physical force of attraction known as hydrogen bonding. Likewise, let us draw another force of attraction. Eventually, we cannot say that these are also examples of hydrogen bonding. Let's say in 360 view, if we are going to view hydrogen in 360 view, then at that moment the force of attraction which appears of oxygen with H of hydrogen in the H2O structure will be having four hydrogen bondings. You will have four hydrogen bondings. There is H, there is also H. Likewise, in this case, in a 360 view, in a 360-degree view, we can see a four hydrogen bonding covered within one H2O molecule. And this is about the hydrogen bonding. One more thing, hydrogen bonding here, when it comes to its strength, it is the strongest physical force of attraction or secondary force of attraction or van der Waals force, and that strongest van der Waals force is around 22 times weaker 22 times weaker than covalent bond, or in other words, it is 5 to 10% in strength as that of the covalent bond. Now when it comes to some sort of applications are in such a manner that here, we are having its applications in chemical as well as biochemical fields, such as water, which is an essential aspect of human beings, is not only used for drinking but it is also used for various purposes, which is only having its highly compatible and adaptable behavior, and its ability to exist as liquid due to the presence of hydrogen bonding. After that, many of the macrobiomolecules such as protein, DNA, benzene, all of the organic molecules are having hydrogen bonding. Let's suppose if we talk about C2H5OH, let's talk about ethyl alcohol, right? This is ethyl alcohol, and that ethyl alcohol basically having OH, oxygen and hydrogen, which means there is a hydrogen bonding, right? After that, how many hydrogen bondings are there? one hydrogen bonding. Likewise, if you talk about another structure, let's talk about H2O. Now H2O has two, how many hydrogen bondings? Here in a single view it has two hydrogen bondings. So here it is having high amount of hydrogen bonding, H2O more amount of hydrogen bonding. Actually we are considering that in a 360 aerial view. So in that case, H2O having four hydrogen bonding, it is having one hydrogen bonding, which means H2O has a stronger intermolecular forces of attraction, due to which it is having higher melting point, higher boiling point, higher surface tension, higher viscosity, as well as less amount of vapor pressure, less evaporation, high polarizability, high stability, less reactivity as compared to ethyl alcohol. So this is how we compare it. After that, when it comes to other factors, cleaning action of soap and detergent is based on hydrogen bond formation between the polar part of detergent and the soap with water molecules, and this phenomena is known as addition. Addition occurs when there is water molecule on one hand side, and on the other hand side there is an other polar molecule which is not water but another polar molecule that causes to form uh, force of attraction, which is you know known as the adhesive force of attraction. That adhesive force of attraction causes to form water to have an increase in its soaking power. We're going to discuss that later. After that, paints are viscous materials. They easily form a smooth layer on a surface. The adhesive action of paints is developed due to hydrogen bonding, and that hydrogen bonding is basically what it is developed in terms of water and as well as in paints. Moreover, fabric of clothes is made up of fibers such as silk, polyester, nylon. Rigidity of tensile effect in its threads is developed by the hydrogen bonding. Now, coming to the concept of hydrogen bonding to explain the properties of water, we know that water has many of the properties which remain a bit of unclear to us in daily life, but we are going to discuss here how to acknowledge them from a chemical perspective, such that if we are having high specific heat, if there is a high specific heat, then firstly let us consider what is the specific heat capacity. It is the amount of heat energy which is required to raise the temperature of 1 gram of any substance by 1 centigrade. Such that if there is 1 gram of any substance, and if I'm going to raise its temperature by 1 centigrade, then at that moment the amount of heat which would be absorbed by that substance to raise its temperature from 14 centigrade to 15 centigrade, or 15.5 to 16.5 centigrade, would be considered as high specific heat capacity. And water does not warm or cool rapidly. Reason behind it is that it is having high amount of specific heat. Water does not warm or cool rapidly. We might have seen that whenever we tend to uh, uh, you know go in, let's suppose if we talk about taking bath. So while taking bath, we usually see that the water does not immediately uh, absorb the amount of heat if there is too hot outside, or immediately become very very cold when there is too cold outside. The reason behind it is that it is having high amount of specific heat capacity, which is due to the hydrogen bonding. Its specific heat capacity is around 4.28 joule per gram Kelvin, if I'm not wrong. Joule per gram Kelvin, this is a specific heat, which is again a large one. And apart from that, when it comes to its high specific heat capacity, whenever we see boiling water does not boil immediately. If you're going to boil water, then it will take initially a lot of amount of time in order to increase its temperature to a higher extent. The reason behind it is its high specific heat of capacity. So in that case, the amount of heat which is absorbed is responsible for it. After that, high specific heat of capacity has marked effect on weather, such that it plays important role in moderating the temperature of Earth's surface, such that if we talk about two different areas, we usually see that the coastal areas are not having neither having a higher temperature during summers, nor are having a low temperature or cold temperature during winters. Reason behind it is that during the hot temperature, when there is, there's summer season going on in near the coastal areas, then at that moment, uh, whenever the amount of heat which is poured over water, because the area is near near coasts or seas, so at that moment when the amount of heat is poured over the water present there, that large amount of heat which is being poured over the seas is being immediately absorbed by the water molecules, as a result of which when the heat is absorbed immediately by water molecules, that the water doesn't immediately tends to evaporate itself and raise its temperature. It tends to absorb the amount of heat uh, till the extent it can raise its temperature, such that when it absorbs that much amount of heat, it causes to more regulate or absorb much amount of heat by you know raising a small amount of its temperature, which means much amount of heat which is being poured over the coastal area is being absorbed by the water without raising much of its temperature, as a result of which it will cause the temperature of water to increase to a little extent, as well as absorb much amount of heat, due to which temperature within the coastal area will tend to remain regulated. Of course, there will be some sort of fluctuation, but overall that will remain regulated during daytime, and when there will be nighttime, the water will now tend to release its temperature, release its heat in order to decrease the temperature. So at that moment, when water will molecules, after having the amount of heat stored within them, now will tend to release the heat, that will cause to neither uh, make the night time uh, you know neither make the night very cold, as a result of which it will lead to moderate and regulate the temperature to that extent, as a result of which the temperature would be regulated, and then at night time there will be neither a cold temperature, and during daytime there will be no hot temperature, due to the presence of water. And reason behind it is a hydrogen bonding. On the other side, if we consider desert desert area basically, it is having rocks and sand over there. So at that moment when there is rock and sand over there, we know that rock and sand are having less amount of specific heat, as a result of which this less amount of specific heat uh, causes to raise their temperature immediately during daytime, due to which at daytime the temperature starts to rise immediately to a harsh level, while during nighttime the temperature starts to decrease uh, immediately due to low specific heat capacity. So this is a point to be pondered. After that, when it comes to high boiling point, water is having a high boiling point. Reason behind it is that each molecule consists of two polar hydrogen atoms and one oxygen atom with two non-bonded pair of electrons. Thus, a water molecule can maximally have four hydrogen bonds in three-dimensional space. Hence, extra energy is required for breaking the hydrogen bond. That is why, due to the four hydrogen bondings, water boils at a higher temperature, 100 centigrade, as compared to other liquids, such as if you compare it with ammonia. Let's suppose ammonia is having its temperature around 60 centigrade, boiling point. Sorry. After that, when it comes to ether, East, Easter, right? Easter having 35.5. After which, when it comes to benzene is having around 80 centigrade. So uh, water is having the highest because of maximum number of hydrogen bonds. On the other side, if we compare hydrogen fluoride, uh, in the case of hydrogen fluoride, hydrogen bonding among hydrogen HF molecules is stronger due to high electronegative fluorine atom, but boiling point of hydrogen fluoride is quite lower than water. Reason behind it is that it is having less number of hydrogen bonding, because in fluorine structure, let us try to draw the structure. Here there is fluorine, there's one hydrogen bond, and possibly there would be another hydrogen bond formed between another molecule, due to which there will be less amount of hydrogen bond formed, due to which there will be two amount of hydrogen bond formed, while in water there are four hydrogen bonding, which means still it is having less hydrogen bonding and higher boiling point. And now, high density of water. High density of water is due to again the presence of hydrogen bonding, and this is the reason it is strongly attracted and occupies less volume. Since density is inversely proportional to volume, the density of water is relatively high. At 20 centigrade, the density of water is 1 gram per centimeter cube. One more thing, the density of water is maximum at 4 centigrade. We are going to discuss that. And then marine life survives underwater due to the high density of water, such that if we are having, let's take an example. If we talk about two seas, we are having two types of water. One is the fresh water, second is the marine water or sea water. Fresh water is having more concentration of salts, and sorry, fresh water is having less concentration of salts, more concentration of water. And on the other hand side, marine water is having more concentration of salts, less concentration of water, due to which marine water basically has a huge amount of concentration of salts, due to which there is on one hand side hydrogen bonding of water molecule itself. And apart from water molecule, there's also other types of bonding with salt, such that there can be dipole ion interaction, there can be dipole induced dipole interaction. Likewise, there can be some gases, due to which there can be dipole induced dipole interaction. So in that case, there will be a lot of bondings formed in marine water, due to which there, due to high amount of bonding, high amount of attraction, there will be high density of marine water. Due to high density, there will be less volume of marine water. Contrary to marine, we are having fresh water. In fresh water, there is less amount of salts, due to which there will be less quantity of such type of forces, and there will be more amount of hydrogen bonding. As a result of which, the more amount of hydrogen bonding will lead to only form a single type of hydrogen bonding, and as a result of that, there will be low density and there will be high volume. So the ships we are having, I mean the cruise ships are able to uh, you know float in marine water only. The reason behind it is that the marine water is having high amount of density, less amount of volume, so that it cannot sink within the water. If we are going to float the same ship within a fresh water, then it will instantly sink. Reason behind it is that it is having low density, high volume, due to which it will ultimately lead the highly densified, or denser uh, cruise to sink within the fresh water. Now coming to another part, which is highest viscosity. Hydrogen bond is the strongest attractive force again, and as a result of high amount of hydrogen bond, multiple hydrogen bond in three-dimensional space, it is quite closely attached with other molecules, due to which there is high viscosity as compared to other molecules of water. Now coming to another part, surface tension. Surface tension, what is surface tension? It is a characteristic. It is just like if we talk about the pull or attractive pull of the upper surface of water molecules by the downward molecules is known as the water surface tension, is known as surface tension. Attractive molecules pull of upper surface by the downward surface is known as surface tension. And here surface tension basically is caused in such a manner that the downward molecules having no attractive amount of forces will tend to attract. Now the downward molecules tend to attract the upper molecules, the surface of the water molecules, such that the surface of the water molecules will tend to act like a stretched membrane, just like it will look like a stretched membrane due to the attractive forces, and which will cause to form a surface tension. And that surface tension, which uh, is supposed to cause to make it like a stretched membrane, which is known as surface tension. And that surface tension is purely due to the strong cohesive forces, which are due to the hydrogen bonding between the water molecules. After that, when it comes to viscosity, it is the internal resistance. It is the internal resistance, or in other words, it is the resistance to flow of the liquid, due to the multiple layers present within the water, multiple hydrogen bondings as well as multiple layers. It causes to stop the flow, make water more viscous. After that, finally, we are having anomalous behavior of water, such that if we talk about hydrogen bonding in water leads to some unusual and unique behavior which is seen in daily life. Such that if we talk about the behavior of water above 4 centigrade, hydrogen water molecules above 4 centigrade have normal behavior like other molecules, such that they contract upon cooling and expand upon heating. But if we talk about their behavior below 4 centigrade, then at that moment their behavior is inverse. They expand upon cooling and they contract upon heating. So let's see how. uh, First and foremost, it shows highest density at 4 centigrade, and below this at this temperature its volume increases instead of decreasing. This anomalous behavior of water can be attributed by arrangement of hydrogen bonding among water molecules. Hydrogen bonding in water above 4 centigrade is temporary due to high thermal energies. Thus water molecules can easily break their hydrogen bonding and quickly reform new hydrogen bonding with some um, other molecules in the neighborhood, such that if we talk about uh, the structure, let's suppose if we are having water molecules. Now water molecules, this is let's suppose this is the condition at 4 centigrade. At 4 centigrade there is maximum amount of temperature, maximum amount of density, such that maximum amount of density is there, less amount of volume is there. Less amount of volume is there. Less amount of maximum amount of density, less amount of volume is there. Above 4 centigrade, above 4 centigrade, the contraction will lead, the heating of the water molecules causes expansion, such that they expand upon heating, and likewise they contract upon cooling, because it is a normal behavior. Just like if we are providing heat, they will have kinetic energy increase, due to which the molecule will tend to run away, their motion, their speed will start to increase, the rate of collision will start to increase, and thus they will tend to remain away from each other, and thus as a result they will cause to form expansion of their structure. Same goes with cooling. If we are going to decrease the amount of heat, then they lose their kinetic energy, and thus they come closer to each other, as a result of which they form attractive forces, and thus they lead to the condition of cooling. But when it comes to below 4 centigrade, below 4 centigrade uh, below 4 centigrade, uh, as the water molecules are further cooled down, let's suppose if these are the water molecules which are further cooled down. So these water molecules, upon further cool down, will lose further of their kinetic energy. As they will lose further of their kinetic energy, they will tend to come near to each other. They will tend to come near to each other, and as a result, as they will tend to come near to each other, they'll tend to come near to each other, because of course contraction is occurring due to the loss of kinetic energy due to cooling. Now, when they'll tend to come further near to each other at 4 centigrade, below 4 centigrade, at 4 centigrade, they are nearest to each other and having the highest density, least volume. But if they're coming now nearer to each other below 4 centigrade, that will lead them to that will lead them to repel their electrons. As we can see, there are electrons present over there, electron cloud around them. So when they'll try to come further nearer to each other, they will now tend to repel each other due to the repulsive forces which are generated between the two different electron clouds of two different atoms. As a result of which, when they'll tend to now further contract uh, due to the cooling effect, they will now, instead of contracting, they will tend to repel the negative charges which are accumulated in case of closely packing the molecules together. As a result of which, this repulsive force will tend to now, instead of contracting, will cause the expansion of the water molecules. And thus, as a result of expansion, the water molecules, instead of being quite near to each other, will tend to move away. Even though they will tend to move away, and as a result, when they will tend to move away, their space will increase, volume will increase, and thus density will start to decrease. And this process, this behavior of what is known as anomalous behavior. And one more thing, that uh, at 0 centigrade, if you're following the same behavior, contracting it again and again and again, it will cause to generate more of the repulsive forces, as a result of which its density will gradually remain decreased, time by time, as we are decreasing in temperature. At 0 centigrade, at 0 centigrade, at 0 centigrade, the temperature, the uh, the water molecules will have the lowest density, such that they will be having the lowest density, and they will have the highest volume, and at that moment this structure which they will form will be in the form of because it's their freezing point. So because of the hexical of the freezing point, they will now be converted into ice at 0 centigrade, but with the highest amount of volume and lowest amount of density, which means this is uh, how the structure will be formed, such that at 0 centigrade ice will be formed and there will be a hexagonal arrangement such that there will be a geometry because it is, you know what, it is a crystalline solid. So hexagonal arrangement would be there, hexagonal arrangement would be there. So such that this hexagonal arrangement would be there at 0 centigrade. There will be formation of ice, and that ice will uh, have a density which would be least which would be having the least density of H2O and highest volume of H2O. And this is how, you know, uh, a marine life survives underwater whenever there is cold temperature in, cold areas such as -1, -2, or other temperatures at that moment. Uh, Even though water, the marine life under the water is remaining safe, is under its, undergoing their life cycle, but on the upper surface the water molecules tend to the upper surface the water molecule tend to form a layer of uh, ice because of the consistent consistent lowered temperature, due to which there will be high amount of formation of forces of repulsive forces. High amount of repulsive forces form, as a result of which expansion will occur due to these repulsive forces. As a result of these repulsive forces, expansion will occur, due to which it will cause to form a lattice structure of ice with the lowest density, highest volume, and thus this process will be known as anomalous behavior of water. And a common example written in our book, that here, as you can see, in the cold region, water supply in the pipelines burst if not properly insulated. The reason behind this is the anomalous expansion of water, because below 0 centigrade the water molecules tend to expand, as a result of which, if the pipe is not properly insulated, then the pipe will, in case, can be bursted due to no proper insulation, because of the anomalous behavior of water uh, in cold areas before the temperature of 4 centigrade. And apart from that, when it comes to some other characteristics, here the volume in the form of ice, water molecules are arranged in the more regular hexagonal patterns in the manner that empty spaces are created in the structure of ice, and its volumes expands up to 10 centigrade, 10%. The low density of ice can be seen when ice floats, and here, as you can see, this is a structure. And now you might be wondering why this anomalous behavior only occurs in water. Reason behind it is that hydrogen bonding in water are maximum. Four hydrogen bondings are there. Due to the presence of four hydrogen bondings, the due to the presence of four hydrogen bondings with the water molecule, these four hydrogen bonding, as seen in the diagram in the water molecule, will tend to, you know have a maximum number of hydrogen bonding, as a result of which it is having the anomalous behavior, and this is the reason why repulsive forces are generated. Now coming to other part, which is about the physical properties of liquids. What are the physical properties of liquid? First and foremost, we have previously discussed what are the some of these includes evaporation, vapor pressure, as well as boiling point, as well as there is surface tension, viscosity, and some other properties are there as well. As well, let's discuss them one by one. First, when it comes to evaporation, we have seen that, you know whenever we are, hanging out outside clothes, moist clothes in the sunshine, tend to you know they tend to become soaked. The reason behind it is that there is a process occurring which is known as evaporation. So evaporation, it is defined as a process in which, at any given temperature, a certain number of molecules in a liquid possess sufficient kinetic energy to escape from the surface, such that they possess sufficient kinetic energy to escape from the surface only, which means they are possible to escape from the surface only, which is known as evaporation. As you can see in the diagram, molecules tend to escape from the surface only. Let's suppose if we are having a container, in container I am having water, and that kind of water now is supposed to have, let's suppose there's temperature outside which is around 37 centigrade, 35 centigrade, let's suppose. If I'm keeping water at 35 centigrade, let's suppose, at that moment it's not the boiling point of water, and water is neither boiling. The reason behind it is that it is not having its boiling point. So here, as water is there, 35 centigrade is there, the water will now have a condition that the upper layer of water molecules, upper layer of the water present within the container, upper layer of water present within the container will tend to absorb the amount of heat, will tend to absorb the amount of heat energy which is present within its surrounding, such that when it will tend to absorb the amount of heat present within its surrounding, the water molecules which are present on the surface after absorbing heat which is present on their surroundings will cause to have their kinetic energy increased. As a result of increasing the kinetic energy, that will cause the increase in the kinetic energy, and that increase in their kinetic energy will cause to increase their speed and collision rate, due to which they will now tend to break their attractive forces and run away from their surface into the environment and in the form of gaseous vapors. And at that moment, this process, which would be occurring at any given temperature, would be known as the evaporation, which is only occurring at the surface. You might be wondering, why does it not occur in all of the molecules which are present below the surface? A reason behind it is that the molecules below the surface are not in contact, are not in exposure to the environment. They are not in exposure to the environment, as a result of which they are not able to absorb the amount of heat, absorb the heat energy from the surrounding, as a result of which evaporation cannot occur in the molecules downward that. And now one more thing, that what are the factors on which evaporation is dependent upon? Evaporation is dependent upon a number of factors. First and foremost, it is not dependent on mass, whether we are taking 10 kilogram or 5 kilogram, 5 liter or 10 liter or 1000 liter. There's no need of mass. Now when it comes to some characteristics, its characteristics are such that it is dependent on a number of factors such as surface area, intermolecular forces, temperature. And here it is basically an endothermic process. It is an endothermic process such that it requires high amount of energy, heat energy. It requires some sort of heat energy from the surrounding, which means it absorbs the heat energy from the surrounding in order to evaporate the molecules. And as a result, this amount of heat energy which is absorbed by the liquid molecules, it will cause to give a cooling effect to its surrounding, due to lowering the amount of heat content of the surrounding, due to which temperature of the surrounding will also remain decreased by the process of evaporation occurring in the surrounding. Therefore, the average kinetic energy of remaining molecule decreases. As a consequence, the temperature of the liquid falls. For example, when we pour some ethanol on our palm, we feel coolness. Reason behind it is that the ethanol basically absorbs heat from our skin and then evaporates, as a result of which it gives us a cooling effect. Endothermic process is occurring as a result of evaporation. And on the basis of evaporation, we are having two different types of liquids. On the basis of evaporation, we are having two different types of liquids, which includes, we are having two different types of liquids, among which number one is the volatile liquid, number two is non-volatile liquid. Non volatile liquid. Volatile liquid, first and foremost, is one which is having high amount of fumeration power, and non-volatile liquid which is having less fumeration power, right? After that, when it comes to volatile liquid have the characteristic that they can evaporate readily. They can evaporate readily. And non-volatile liquid which cannot evaporate readily. The reason behind why they evaporate readily is their fumeration power, and the reason they do not evaporate readily is the less fumeration power in non-volatile liquids. And apart from this, when it comes to certain factors, that uh, what is the example? Volatile liquids includes petrol, gasoline, and other sort of liquids, acetone. These are some volatile liquids. Non-volatile liquids, H2O, it does not evaporate readily. For that, it requires some sort of external environment, high amount of heat condition in order to evaporate it. After that, when it comes to petrol, if we consider petrol, we also see in our daily life that volatile liquids have more readability to catch fire, and that high amount of readability to catch fire of volatile liquids is due to the reason that whenever volatile liquids evaporate due to high fumeration power, they evaporate readily in a continuous chain as a result of which continuous chain as a result of which they are able to uh, you know uh, whenever they are able to evaporate readily fastly in a continuous chain, they if one molecule catches fire, then the entire solution catches fire because of the continuous chain which is formed in which they are you know evaporating. Likewise, in non-volatile liquids there will be evaporation in certain conditions, but that would not be in a continuous chain. That is why if we talk about water, water cannot catch fire easily because uh, it is it is not able to evaporate itself in it is not able to evaporate itself in a continuous chain. Apart from that, when it comes to certain factors, when it comes to other factors, there are certain factors which influence the rate of evaporation, such as surface area, intermolecular forces, and temperature. If we talk about surface area, the larger amount of surface area, the the tendency of molecule to transfer from liquid to air, because more amount of surface area will require more molecules to come in exposure to the environment, due to which more amount of molecules will absorb heat and more amount of molecules will tend to escape from the surface, as a result of which the rate of evaporation will be ultimately increased. This is due to the fact that greater surface area allows more molecules getting energy from the surrounding and escape into air. That is why water is spilled on floor evaporates more readily as compared to the same amount of water in the container. And opposite to the process of evaporation, there is a process known as condensation. It is basically an exothermic process, and this basically happens when the gas molecules, if we talk about as the example is given, water droplets are quickly formed at the outer surface of a cold bottle when it is taken out from the refrigerator. This is because of the process condensation occurring, such that the water molecules lose their kinetic energy due to the high amount of unstability. They lose their kinetic energy, as a result of which the gas molecules start losing kinetic energy by striking at the cooler surfaces and change into the liquid state. Oops, change into the liquid state on the outer side of the water bottle, and this is an exothermic process. After that, when it comes to intermolecular forces, evaporation depends upon the nature of intermolecular forces present among liquid molecules. If we talk about acetone evaporates quickly than water at the same temperature. Reason behind it is that acetone is having a less amount of intermolecular forces, less stronger intermolecular forces known as London dispersion forces, and then hydrogen bonding is a stronger intermolecular forces present in water, due to which it is having less rate of evaporation. And one more thing to consider over here is about which force is having the highest amount of intermolecular, which force is having the most strongest. All right. So uh, I would like to just simply mention the strongest force from first to second, strongest first, and weakest fifth. Right. So strongest force among them is hydrogen bonding. Then we are having the second number strongest is dipole dipole, and third number strongest is dipoline. Fourth number strongest is dipole induced dipole, and fifth number strongest is induced dipole instantaneous dipole, which means the weakest is London dispersion forces. So in that case, according to the to this data, the London dispersion forces are weaker, due to which they are having the highest evaporation rate. Apart from which, temperature, it's obvious that if we are going to increase the temperature, more amount of molecules will gain the kinetic energy, increase their more amount of molecules will absorb the heat, and thus kinetic energy will be increased, and they will tend to escape from the surface, and they will be able to escape easily from there, due to which evaporation will be increased. Vapor pressure, what is it? When we, if we take a container in which there is a liquid, and it is enclosed in a tightly covered container, and at that moment, when we start to increase its temperature, at that moment, uh, when if we take a container, let's suppose, let's take the diagram which is given. Now in that container, if we are having, water, let's suppose, and at that moment evaporation is occurring, water at a given temperature, evaporation is occurring, as a result of which, at a given temperature, that evaporation is occurring will cause the water molecules to will cause the water molecules to it will cause the water molecules to evaporate and escape from the container. But since the container is tightly closed, it will not be able to escape from the container, and as a result of this, the molecules will not be able to escape. The molecules will tend to accumulate within the container, and as they will accumulate within the container, many of the molecules will tend to come in contact with the liquid. They will tend to come in contact with the liquid, such that these gaseous vapors will tend to come in contact with the liquid. So at that moment, when these gaseous vapors will tend to come in contact with the liquid, they will tend to you know uh, be attracted by the liquid, and thus they will tend to convert their state of gas vapors into the liquid. And at that moment, this process, when the gaseous vapors will be converted into liquid, this would be known as condensation. This would be known as condensation. This would be known as condensation, such that when the gaseous molecule will rejoin the liquid, at that moment they will tend to lose they will tend to be attracted by the liquid molecules, due to which there will be condensation process occurring. And at the stage at which the condensation process which is occurring over here will be equal to the evaporation process, it would be known as the vapor pressure. So in beginning, the rate of evaporation is, the rate of evaporation will be faster as compared to rate of condensation. But when more molecules will tend to escape out from the container and will tend to accumulate within the container, then at that moment the rate of uh, condensation will start to increase as well. Then at a certain time, there will be a stage when there will be a dynamic equilibrium established between both of the conditions. Dynamic equilibrium will be established between both the liquid state and gaseous state of the container, which would be known as a dynamic equilibrium, at which the reaction is occurring at the same the reaction would be occurring with certain number of molecules. The reaction will be occurring with the help of same number of molecules. Reaction would be occurring at equal rate but opposite directions, which we have discussed previously as well, and such that the pressure of the vapors at this stage will remain constant and will be known as the vapor pressure of that liquid, such that the pressure which would be exerted by the vapors when they are in equilibrium with the liquid phase at that temperature, that this pressure at that point will be known as the vapor pressure. Vapor pressure is independent of the amount of liquid, but it is dependent on the temperature and intermolecular forces, such that if we talk about its factor. If we are going to increase the temperature, there will be increase in the kinetic energy of molecule, due to which the vapor pressure will be increased. Let's suppose if we talk about vapor pressure of water. Vapor pressure of water is 17.5 torr at 20 centigrade, but at 100 centigrade it is 760 torr, which is a huge difference. The reason behind it is the temperature. Another factor which affects the vapor pressure is the strength of intermolecular forces, such that if we are having high amount of intermolecular forces, then there will be less rate of evaporation, and hence there will be less amount of vapor pressure, due to which vapor pressure will be decreased if the intermolecular forces are increased. Vapor pressure of diethyl ether at 20 centigrade is 172, which is much higher than water. The reason behind it is less amount of intermolecular forces, London dispersion forces, which will cause to increase the vapor pressure, right? After that, when it comes to, as a result, if we talk about boiling point now, boiling point is a condition in which if we are having the vapor pressure, the rate of vapor pressure is equal to the the vapor pressure becomes equal if at any given temperature if at if at any temperature the rate of vapor pressure is equal to the, if at any temperature the vapor pressure becomes equal to the atmospheric pressure, then at that point this temperature would be known as the boiling point of that liquid. When a liquid is heated, more molecules require kinetic energy to escape, and the evaporation becomes more rapid. As a consequence, the vapor pressure liquid increases until it becomes equal to the atmospheric pressure, such that at that point this would be considered as uh, a boiling point when the vapor pressure is equal to atmospheric pressure. When atmospheric pressure is 1 atmosphere, the boiling point is referred to as normal boiling point. Boiling point of liquids depend upon the atmospheric pressure, and it varies at different regions on Earth, such that at sea level the atmospheric pressure is equal to 762, where water boils at 100 centigrade, whereas where the water boils quite easily, as a result of which the food cooked there will have more amount of heat energy entailed within the boiling point of water, due to which there will be more amount of the food will be cooked quite fast, as compared to murky or hilly areas where atmospheric pressure is less than is low, around 700 torr. So at that moment water boils at around 98 or 96 centigrade, which means at that point, due to low vapor pressure, the water will boil at a low temperature, which means less amount of heat will be entailed, as a result of which at in muddy areas there will be the food which would be cooked due to high less amount of heat energy will take more time in order to become cooked. So this is the reason behind it. After that, at normal boiling point, 100 centigrade of water, the food will be cooked easily. However, at higher altitude such as Gorakh Hill, where air pressure is usually low, water boils at low temperature, thus food will take longer time. And likewise, we are having the mechanism of pressure cooker. Pressure cooker steam is prevented to get escaped, as a result of which the atmospheric pressure is ultimately increased within the pressure cooker. As a result of which, when the vapor pressure is achieved, that vapor pressure is able to quickly achieved. The vapor pressure is able to achieve with respect to 1 atmospheric pressure, and thus at that point the water is then able to boil within a pressure cooker more readily. Water is then able to boil within a pressure cooker more readily. Water is then able to boil within a pressure cooker more readily, and the food is because the boiling point obtained would be normal, as a result of which more amount of heat would be entailed within the pressure cooker, as a result of which it will cause uh, atmospheric pressure will increase, due to which the boiling point will be increased, due to which the more amount of heat will be entailed, and thus it will lead uh, the food to be cooked very easily. For example, glycerine boils at 290 centigrade at 760 torr, but it decomposes at that temperature. But if we decrease its pressure, atmospheric pressure, then it boils at 210 centigrade without decomposition. So this is a factor. After that, when it comes to some other uh, things, we are going to discuss about viscosity. Viscosity, basically it is the decrease in the flow of liquids due to the internal resistance among the layer of molecules, such that each layer offers some sort of friction. If we talk about liquids, they are having multiple layers, they are arranged in multiple layers. If there's a single layer of molecules, there's after which there's another layer. Let's suppose if this water is having three layers. Now at that moment, the layer which is in contact with ground, the layer which is in contact with ground will be having, friction, resistance from the downward side of ground, and on the other hand side there will be a friction which would be generated from the upper layer, and that internal resistance of the liquid to flow generated from the upper layer would be known as viscosity. Likewise, if we talk about the viscosity of the middle one layer, viscosity of the middle one layer will be greatest because it is having the internal resistance from the upper side as well as from the downward side. Likewise, if we talk about the outward layer or the uppermost layer is only having viscosity or the decrease in flow or internal resistance from the downward side, due to which resistance is only from the downward side, not from the upward side, as a result of which it is having a less amount of viscosity. So it is simply the resistance in the flow of liquid. And after that, viscosity is a measure of internal resistance of a liquid to flow. It is affected by the following three factors. Number one is the intermolecular forces. If the intermolecular forces are increased, then the viscosity is ultimately increased, such that if benzene, gasolines are there, which consist of non-polar molecules, possess intermolecular forces, possess weak intermolecular forces, and have relatively low viscosity. If we compare polar molecules such as glycerol or methanol, they are having high strong intermolecular forces because they possess hydrogen bonding, so as a result of which they have high viscosity. Water is having more viscosity than acetone because of strong hydrogen bonding present among the molecules and weaker London dispersion force. After that, when it comes to temperature, if it is our everyday experience that if we are supposed to increase the temperature, viscosity is decreased. It is easy to flow honey at a higher temperature as compared to a lower temperature. Likewise, if there is molecular size, if we are increasing the molecular size of the liquid, if we are increasing the molecular size of the liquid, then it will have more of the liquid will, if there is higher molecular size, there will be higher polarizability, due to which more of the molecules will tend to form a stronger intermolecular force of attraction, due to which there will be a higher viscosity. And if there are molecular chains tangled up, then of course there will be more polarizability, more stronger forces would be there, for more stronger forces of attraction would be there, as a result of which the forces as a result of which there will be more stronger forces of attraction, and thus viscosity will be ultimately increased. Apart from which, when it comes to viscosity's unit, its unit in CGS is poise, and we can also write it as centipoise. When it comes to its SI unit, it is Newton second per meter square, and we can also call it as Pascal second. This is all about viscosity. When it comes to surface tension, we have already discussed the liquid molecule attract each other, but intermolecular forces are not, you know, uniform throughout the liquid body, such that if we talk about two molecules of liquid A and B, one molecule A is on the surface and other molecule B is in between the liquid, such that the one which is in between the liquid will be having attractive forces from upper side, by it will be attracted by upper liquid molecule, by a left side liquid molecule, right side liquid molecule, and down side liquid molecule, which means the attractive forces on all four directions are equal. But when it comes to the liquid molecule A will be having the attractive forces from the downward side, from the right side and the left side, but it will not be having a attractive force from the upper side, which means it is having an unequal downward pull, and that unequal downward pull would be known as, that unequal downward pull will cause to attract the liquid to of the or I mean the surface of the liquid to the uh, downward side. This attractive pull will cause to attract the surface of the liquid towards the downward side, as a result of which this will cause to create a tension within the liquid, which would be known as surface tension, which occurs over the surface. And this shows that attractive forces on molecules at surface and inside liquids are unbalanced. Molecules at the surface of the liquid experience more attraction, which works as like a stretched membrane, and it tends to compress the molecules below to the smallest possible area and create a surface tension. Surface tension is the force. It is the force which is acting at right angle on the unit length of the surface of the liquid. It is the force which is acting on the right angle. As you can see, it is a force here. It is a force. It is a force which is acting on the right angle. It is a force which acts on the right angle. It is a force which acts on the right angle on unit length of the surface of the liquid, which is known as the surface tension. Force which acts on right angle on unit length of surface of the liquid, which is known as the surface tension. Apart from which, when it comes to some other parts, I would like to highlight over here is that here uh, surface tension can also be defined in other words as the amount of energy which is required to now, due to the force which is applied on unit length of the surface of the liquid surface is a bit stretched, just like a stretched membrane. Now in order to uh, re de-stretch it, or de-distant it, or de-stretch it, we need to apply some sort of energy in on per unit area of the surface of the liquid, so that it can be again uh, converted or back into its original surface, or again it can be de-stretched or distended. So at that moment, this amount of energy which is required to increase the unit area of surface of the liquid is also known as surface tension in other terms. And physically, uh, in physical terminologies, we can consider its unit in such a manner that here we are having its unit as dyne per centimeter or erg per centimeter square. And here liquids tend to minimize their surface area as much as possible to attain a spherical shape, such that if we talk about, there are two types of liquids. If uh, we are going to talk about this, there are two types of generally liquids, which liquids basically have two forces which are hard. One of the force is this cohesive force, and is the adhesive force. Cohesive force is a one which causes to form uh, one liquid polar molecule to attract with its similar other liquid polar molecule. Adhesive force is the one which is formed between one polar molecule and another polar molecule, whereas cohesive force is the one which is formed in between the polar molecules, and adhesive force among the polar molecules. If a liquid is having cohesive force greater than adhesive force, if a liquid is having cohesive force greater than adhesive force, this liquid which is having cohesive force greater than adhesive force would be known as non-weighting liquid. Non-weighting liquid. Cohesive force greater than adhesive force will be known as a non-weighting liquid. Cohesive force greater than adhesive force, non-weighting liquid, which would be having less soaking power. Soaking power would be less. After that, if we talk about another type of liquid, let's say if we have a liquid which is having its adhesive force greater than cohesive force. If we are having a liquid which is having its adhesive force greater than cohesive force, that would be known as a weighting liquid. It will have more amount of soaking power. Let's take an example of this. If we take mercury as a liquid, mercury is the only metal which occurs in liquid form. And here mercury, basically it is having high amount of soaking power because it is having its cohesive force greater than adhesive force, such that if we whenever we wash clothes, if we are supposed to wash clothes with mercury, then we would not be able to uh, will not be able to soak clothes within mercury. Reason behind it is that the soaking power of mercury is low because of cohesive force greater than adhesive force, as well as if you're supposed to swim in a swimming pool of mercury liquid, then at that moment we won't be able to swim. Reason behind it is that mercury is having high amount of cohesive force, less amount of adhesive force, less amount of soaking power. It is a non-wetting liquid. Likewise, uh, if we are going to utilize it for other purpose, we cannot able to soak it. When it comes to water, water is a no is a weighting liquid. Soaking power is high. Adhesive force is greater than cohesive force, such that when H2O is, clothes are washed, we are able to wash the clothes properly. We can swim in H2O water easily, right? So this is a basic concept behind it. And here the reason, whenever we see the reason behind whenever we see a water drop falling on the ground, it is in the spherical shape. Reason behind it is that The spherical drops in such a manner that when the tap is opened, when the water molecule is attached with the tap, water molecule is attached with the tap, it will be having its adhesive force greater than cohesive force, such that it will be having more adhesive force. There will be generation of adhesive force when it will be attached with the tap, but when it will tend to move down, but when it will tend to move down in free space, in free space there will be no adhesive force because there will be no other polar molecule except water molecule, due to which there will be no adhesive force, but there will be formation of only cohesive force, and that cohesive force will cause the water molecule to decrease its surface uh, decrease its surface area, and ultimately the surface area decrease will be decreased to such an extent that it will create a surface tension, and that surface tension will be decreased in the form of a sphere, because a sphere is having the least amount of surface area, due to which it will be decreased in form of sphere, and that's how the spherical shape of drop is obtained due to the cohesive forces in order to decrease the surface area due to the high amount of surface tension of water. And same goes for liquid mercury. After that, when it comes to other part, attractive forces between the molecules of same type are called cohesive, and between molecules of different types are known as adhesive forces. For mercury, when which confined to a glass tube does not weight the water due to its strong cohesive forces as compared to adhesive forces. This is why it is used in thermometer. It is utilized in thermometer. Reason behind it is that it is having high cohesive forces, due to which it is not able to uh, soak itself with the thermometer tube, but it is able to only move up and down due to the absorption of heat within the thermometer. Thus it does not soak itself or form adhesive forces, rather it just form cohesive forces and moves up and down within the thermometer, so that we are able to recognize whether the body's temperature is increased to the certain extent or not. After that, when it comes to some other part, we are going to discuss about uh, capillary action. Capillary action is a short topic in which if we are supposed to dip one end of a clean capillary tube in a bigger container than in a beaker, let's suppose. So the water molecules will tend to raise to a certain height. This is known as capillary action, which is due to the soaking power of water, such that if we are having soaking power of water, the water will tend to having its soaking power, adhesive force greater than cohesive force, will tend to have its water molecules be form an interaction with the glass tube, as a result of which that this interaction will be known as adhesive force, and as a result of that adhesive force being generated, it will cause the water molecules to uh, remain to come above the capillary tube and increase its height. The capillary action is due to the combined effect of cohesive force among liquid molecules and adhesive force between liquid molecules and the wall of tube. So later rises in the capillary tube because its water rises in the capillary tube because its adhesive forces become stronger in a tube of smaller diameter. So this is the reason that even though capillary in the capillary action, both adhesive and cohesive forces are acting, adhesive forces uh, are having greater action. Reason behind it is that there is smaller diameter of the tube, and examples of this includes blotting paper, spreading of ink in blotting paper is example of this, and rise of oil in the wicks of lamp is example of this. Rest, when it comes to energetic of phase change, energetic of phase change is simply defined as. Now coming to energetic of phase change. Now energetic of phase change here is in such a manner that, as you can see, what is energetic of phase change? Energetic energy phase means transformation. Here change means transformation. Here transformation, the energy which is required to cause physical transformation is known as energetic of phase change. Now let us explain it here. Energetic of phase change, such that, as you can see, oops, energetic of phase change. So if we talk about solid, there are three states which we are considering over: solid, liquid, and gas. Not discussing further states, okay? So liquid, gas, such that if we are converting solid into liquid, this process is known as melting. If we are converting liquid into solid, this process is known as uh, converting liquid into gas. This process is known as boiling, uh, or we can also call it as vaporization or evaporation. Boiling, vaporization, or evaporation. Boiling, vaporization, evaporation, let's suppose. And here we are having melting. All right. After that, if gases, now on the other hand side, if liquid is converted into solid, this is known as freezing. And if gas is converted into solid, gas is converted into liquid, gas into liquid will be known as condensation. Likewise, if solid is directly converted into gas, sublimation. If gas is converted into solid, deposition. So these are some reactions, physical transformations which occur in order to change the state of matter. Now, if we talk about converting solid into liquid, melting, or you can also call this as fusion, right? So here, if we talk about you know endothermic processes, now the processes among them which are endothermic will be represented by a red mark, and those which are exothermic will be represented by green mark. So red mark one, so melting is an endothermic process, liquid melting is an endothermic process, boiling is an endothermic process, evaporation vaporization is an endothermic process, and sublimation is an endothermic process. But when it comes to other processes such as freezing, freezing is an exothermic process. It gives a cooling effect, it gives an heating effect. Endothermic process give a cooling effect, and exothermic give a heating effect to the surrounding. And here on the other hand side, if we talk about deposition, it's exothermic process, and condensation is an exothermic process. These are some basic energetics of phase change. Apart from that, when we come to ideally discuss each and every one, when it comes to the endothermic processes only, molar heat of fusion, molar heat of fusion is one which I discussed right now, which is in such a manner that if we are going to discuss, if we are to discuss the conversion of 1 mole of a solid, if you discuss if we have to discuss the amount of heat which is required or absorbed in order to convert 1 mole of a solid into liquid at its melting point and at standard conditions such as 25 centigrade and 1 atm pressure, then this uh, heat of fusion will be known as molar heat of fusion. And that molar heat of fusion is of ice into water is given 6.02 kilojoule per mole. When it comes to uh, a question arises that whether the temperature rises or not. So the temperature does not rise during this condition because the amount of heat which is supplied will will be utilized in order to break the physical forces of attraction. So in that case, in order to break the physical forces of attraction, in order to break the physical forces, in order to break the physical forces of attraction, the an amount of heat given will be consumed, due to which this process would be known as uh, molar heat of fusion. This heat would be known as molar heat of fusion, process would be known as fusion. So in this case, temperature will not be rising. When it comes to molar heat of vaporization, the amount of heat which is required to convert 1 mole of a liquid into its vapor at boiling point is referred to as the molar heat of vaporization. And again, standard conditions are required such as 1 atm pressure and uh, 1 atm pressure and 25 centigrade temperature. And again, if we talk about the rise in temperature, not rise in temperature will occur only the amount of heat will be absorbed in order to convert from its solid state into the liquid state. Here water is converted into its vapor sorry liquid state into the gaseous state, gaseous vapors. And here the amount of heat is given by 40.7 kilojoule per mole. Again, if we talk about molar heat of sublimation, this is the amount of heat which is absorbed when 1 mole of a solid is directly converted into vapor without going through the liquid state at standard conditions such as 25 centigrade temperature and 1 atm pressure, which is known as molar heat of sublimation. For example, when dry ice solid carbon dioxide is converted into its gaseous form directly at atmospheric pressure is known as 25.2 kilojoule per mole. Now, when comparing all of these heats, we can create a chart such that the heat of sublimation is greater than heat of vaporization because it includes direct conversion of solid into gas. But again, there would be a consideration that heat of sublimation will only occur in those solids which are having London dispersion forces. This will not occur in all of the types of solid, as we have studied that all of the solids have different types of forces such as metallic forces of attraction, ionic forces, covalent forces. But the forces here which would be causing them, these solids would be occurring in molecular solids which are having London dispersion forces, due to which there might be a consideration, but again, direct conversion from solid to gas requires more amount of energy. So in that case, we can write heat of sublimation greater than heat of vaporization greater than heat of vaporization greater than heat of fusion. So these are the amount of heat in a single chart. Rest, when it comes to liquid crystal, it is a short topic. Liquid crystal, basically it is a state of matter. It is a turbid state, milky state, or it is a fuzzy state, or it is uh, a middle state, semi-solid state, which is between liquid and solid. It was first discovered by Friedrich Rantzer, and he, while he was examining some physico-chemical properties of derivatives of cholesterol, among which he experimented cholesterol benzoate. He basically knew that at 175 78.5, he knew that at 178.5 centigrade, the cholesterol benzoate will be uh, vaporized, which means it is its boiling point at which it will be boiled. But instead of boiling it at 178.5 centigrade, he started to boil it at, he gave it the condition of 145.5 centigrade. At that point, he obtained a state of matter which was neither a solid nor a liquid, which means it was having the characteristics of both liquid as well as characteristics of both a crystalline solid, such that uh, that solid was a milky, fuzzy, turbid state which was known as the liquid crystal. And that was having characteristics of both liquids as well as solids, such that it was having geometry, it was having isotropy like liquids, it was having geometry, it was having geometry like liquids, such that all solids are having different types of geometries, but here liquid crystals are only having one type of geometry, which is a rod like geometry, rod like crystal, single rod like crystal geometry, single rod like crystal geometry, linear rod like crystal geometry of every liquid crystal. And apart from that, they had some liquid like properties, that they had fluidity, they had viscosity, they had you know such properties such as fluidity, viscosity, as well as they had optical properties found in crystalline solids. So these were some certain amount of properties which were present in both of these. Now, when it comes to liquid crystal, the liquid crystal basically, when it comes to the cholesterol benzoate, particularly cholesterol benzoate is having its liquid crystal properties in three major stages. Thematic, three types of formations of crystalline structure is there. Actually, the crystalline structure is same. There would be a linear rod-like structure, but in cholesterol benzoate, on the basis of disorderly arrangement of the atoms, we are going to characterize into three major formations: thematic, nematic, and cholesteric. Thematic, nematic, and cholesteric. Such that if we talk about thematic, thematic is a less distorted stage. It is less distorted stage, less distorted stage. But when it comes to nematic, nematic is a more distorted stage, such that more of the molecules are distorted. Let me just try to make it a bit distorted. More of the molecules are distorted, whereas cholesteric is the most distorted stage. Molecules are completely distorted, no proper arrangement. I mean, more distorted, most distorted stage. Of course, it would be not as distorted as liquid, but they are most distorted stage. This is the case. And here the temperature at which the boiling point of the uh, cholesterol benzoate is 178.5, and for its state to form a liquid crystal is 145.5. Use of liquid crystal are very common. LCDs, liquid crystal display, in which we are having its use, in temperature sensors and thermometers and other devices to measure body temperatures, are basically having liquid crystal. As well as if we talk about uh, devices such as, nowadays the diagnosis of cancer as well as blockage of veins and arteries can be examined with the help of liquid crystal, such as liquid crystal, when absorbing high amount of temperature, high amount of heat, will cause to change its color. So whenever we are supposed to uh, paint the entire patient's entire body with liquid crystal, the part of patient's body which will be having cancer would be having an inflammation and a high amount of heat generated at that part, due to which the liquid crystal, among absorption of that amount of heat, will cause to change its color, as a result of which it will indicate that the person is having cancer in that particular part of the body. So in that case, liquid crystal is also important in medical uses for uh, blockage of identifying blockage of veins, arteries, as well as uh, examination of different types of tumors and cancers. As well as they are also utilized in hydraulics because of their high viscosity, and they are also utilized in chromatography techniques as solvents in order to distinguish and separate out different types of molecules and compounds. And this is all about this topic. I know it was a bit long, but this is all about today's video. Hopefully, we'll meet again in another video.